Good evening, everybody. How are you all feeling today?
Woo!
Should we try that one more time? For those of you online, I got silence, which means I just crashed and burned with regards to that opening. How's everyone doing today? Okay, that was a little bit better. Are you all excited to hear something about rocks? Okay, now this is getting better. So this is our second public lecture that we're running at the moment. And Fred and myself, together with a fantastic team of Gege and many others who are in this room, have put together a series of lectures welcoming the public into earth science and engineering. Because Tina, how old are we now? We're just 25 in this department. Tina is not 175 years old. We need to hasten to add. So Tina is our head of department. If anybody wants to speak to her later, please feel free to go and seek her out. Hint, she really likes speaking about climate change. So if you want an opener to speak to Tina, go and speak about climate change. So it's our 175th anniversary, and we've put together a whole series of different lectures trying to showcase some of the amazing research, but also teaching that we've got going on within the department.
Yep. And so today's lecture is on geohazards, and we've got a kind of brilliant illustrative lineup for you. We've got Becky Bell, professor in tectonics, Banusha Kugabalan, PhD student in understanding like the effect of stress on rock magnetism, and Ben Conway-Jones, who is an alum who left us in 2018, who now works as an INSAR scientist for Catalyst.
Fantastic. And just to introduce ourselves, Fred, who are you?
I'm an assistant professor in earth sciences.
And my name, and I'm Sarah Gordon. I'm a professor of practice here in the department, which means I get to create havoc because I get to help build that bridge between all the wonderful research that we're doing and the world of industry and the outside world. So together with Fred, we're the ones that are behind the scenes, helping to make sure these lectures all go according to plan. Now, with regards to that, for those of you who are in this room, if you hear the dulcet tones of a fire alarm, it's not going to be a test. No, instead we need to go out that door and into the big courtyard thing outside. Don't worry, we will help you. If anybody else needs water or other refreshments during the course of this lecture, just let us know and we will go and find some for you. We will look after you because you are our guests. At the end of today's sessions, we're going to introduce you to G35, which is a room just back up along the corridor, because in there are more exciting refreshments than water. So please feel free to come and join us for a drink, discuss some of the posters, and also meet our speakers as well. So we very much welcome you into the heart of our department. So with that, I think we will get going with our first speaker. So please put your hands together to welcome to the stage the fantastic Dr. Rebecca Bell, who is an professor in tectonics, and she focuses on understanding fault evolution, as well as different forms of behavior of those rocks from field observations, aka Becky gets to go and travel to awesome parts of the world. Her work includes focus on zones of exciting stuff with regards to rocks in Greece, as well as also going to New Zealand. So please put your hands together for the fantastic Dr. Rebecca Bell.
Good evening, everyone, and welcome to our conversation today about geohazards. So a geohazard is defined as a natural geological process that can cause harm to people, infrastructure, or the environment. The geohazard that I'm going to be talking about are earthquakes. Specifically, I'm going to be talking about a topic that has been described as the most exciting discovery in the field of seismology this century. So if you have previously studied in the RSM or have a geoscience background, you may not have heard of this phenomenon because it's so new, information about it is only now trickling into the textbooks. So earthquakes occur on faults, which are basically cracks in the earth between slabs of rock kilometers thick that have relative motion between them. So for a period of time, those slabs will be stuck, they will be locked. Once enough stress is built up to overcome the friction, they will suddenly slip in an earthquake. And this is called stick-slip behavior. That slip is so fast, it radiates seismic waves and causes shaking. So since the 1960s, we've known that the outer part of the Earth is divided up into a series of tectonic plates, and these are all moving and interacting in different ways. The mechanical properties of these plates are very much like a biscuit. They're rigid. So if I snap this biscuit in half and rub the sides past each other, the deformation, the cracking, the crumbling all happens at the edges. The interior of the biscuit stays relatively deformation free. So the UK, at the moment, we find ourselves in the middle of one of these tectonic plate biscuits, which is why we don't have big earthquakes. You don't have to go very far on holiday, though, to places like Italy and Greece until you are very much at a plate boundary. So I work a lot in Greece with my PhD students, many of them who are here, and Greece is a really good place to see the manifestation of active faults at the surface. So if you're driving north of the Athens area, it's very common to see beautifully polished cliffs like these. These are active faults. How these have been produced is that the block of rock the road is on has moved down relative to the other side. And if you look carefully at that cliff, you can even see scratches on it where that rock has moved down. These faults in Greece are up to about 15 kilometers long. And in an earthquake, they can move by about a meter maximum. That limits the maximum earthquake we'd expect on these faults to around 6.5. The general rule of thumb is the larger the fault, the larger the earthquake we could experience. So these are not particularly big earthquakes, but you may remember the L'Aquila earthquake of 2009 in Italy. That was a magnitude 6.3 on a fault very much like this. So they can be catastrophic. That one killed 300 people. These faults are related to extension, where the tectonic plate is stretching. There are different ways that we can measure the size of an earthquake. You've probably all heard of the Richter scale, which is a measure of the amplitude of shaking a set distance away from the epicenter. I'm going to be using a measure called the moment magnitude scale, which is more related to the area of the fault that slips. So as I've already said, these faults are quite small. So the place on Earth, which has the dubious honor of hosting the largest faults and therefore the largest earthquakes on Earth, thank you, Fred, are subduction zones. These are places where an oceanic plate is thrusting, sliding under another plate. The boundary between these two plates is effectively a gigantic fault. These faults can be hundreds of kilometers wide, thousands of kilometers long. Those faults are called megathrusts, and this is where we have the magnitude 9s and greater. So the 2004 Sumatra earthquake, which you'll remember created that devastating Indian Ocean tsunami, that was an example of a megathrust fault that ruptured a fault 1,200 kilometers long, 200 kilometers wide, way bigger than those little faults in Greece. Okay, so that's all of our background information. Now I'm going to ask you a question. I like to call this a seismic hazard awareness exercise. So I'm going to put you in a situation and I would like you to tell me what you would do. How would you behave? And this is useful if you are going on holiday to tectonic plate boundaries. So it's 2023 and you are sitting in a cafe in a coastal town called Gisborne. Doesn't matter where Gisborne is. It's on the east coast of the North Island of New Zealand, but that doesn't matter. And a moment magnitude 6.8 seismic event happens on a fault 15 kilometers directly beneath you. 15 kilometers is actually quite shallow for an earthquake. So this is a direct hit. So what do? Do nothing, finish your flat white coffee, very popular coffee in New Zealand, dive onto the coffee table and hang tight until it's all over, head for high ground, or run around screaming for there is no hope. So option number one, I'm going to ask you to raise your hands. Anybody very relaxed? A couple. Option number two. Okay, there's going to be, you're going to be quite cozy under these tables. There's a lot of you. Option number three. Hey, that could be smart, right? You've seen this as a coastal town. There could be a tsunami. Option number four. There's always some. Okay, good. What I'm going to show you next are some stills from some CCTV camera footage that shows what happened to the cafe and these people during the seismic event. So if you're of a nervous disposition, you might want to look away now. Absolutely nothing. Nobody died, no buildings fell down, nobody felt anything at all. Not only that, but no seismometers detected anything either. So how can this be? How can we have a moment magnitude 6.8 seismic event that nobody feels? This event and events like it are now called silent earthquakes or slow slip events, and they were only discovered in around the year 2000. They involve as much slip on a subduction megathrust as if a magnitude 7 earthquake happened, but the slip doesn't happen in seconds, it happens slowly over durations of weeks, months, and years. So when the fault is moving that slowly, it doesn't radiate seismic waves and it doesn't create shaking. We know that slow slip events happen thanks to satellite data. So geostationary satellites can measure the movement between GPS stations like this to millimeter scale precision. And when the first GPS data was looked at in Gisborne in New Zealand, it was found that GPS stations were moving by as much as if a large earthquake was happening, but over a duration of 4 weeks without any associated shaking. So this was a completely new discovery not that long ago, around the year 2000. Prior to that, we didn't know that subduction megathrusts could move in this way. That raises loads of questions. Do slow slip events mean that stress is being relieved on the fault? Does it mean a future earthquake is less likely? Does it reduce the seismic hazard? Or could a slow slip event on one part of the fault trigger a large earthquake on another part of the fault? Do slow slip events raise the seismic hazard? There's some evidence that before the 2011 Tohoku earthquake in Japan, that magnitude 9, that slow slip events occurred in the years prior around the part of the fault that eventually slipped. That raises the tantalizing question, could slow slip events one day be used as a bit of a precursory warning sign that a large future earthquake is imminent? So scientists have been studying this new phenomena intensely for the last 10 years, and laboratory experiments have shown us that there are some key parts of the recipe that are important. They suggest that fluids are important, particularly high fluid pressure, effectively lubricating the fault. Another thing the models suggest is that we may need frictional heterogeneity on the fault, bits of the fault zone that are stuck and bits that are unstuck. I'm an observational scientist, so I'm interested in imaging what these fault zones are like, and do we see evidence of fluids, and do we see evidence of heterogeneity? So that's no easy task, because these subduction megathrusts are under 3 kilometers of water, 15 kilometers underground. One of the reasons why Gisborne in New Zealand has become the best natural laboratory in the world to study slow slip is because even though the slow slip events are 20 kilometers deep, that's still a lot shallower than other places on Earth. So the method we choose is seismic imaging. We create man-made sound waves, which we fire at the fault zone. We detect the echoes that return, very much like an ultrasound image of the body. This is a 3D seismic image of the Gisborne slow slip zone. And one of our key findings is that the megathrust fault is not smooth. It's really lumpy and bumpy. And that's because in this area, there are extinct volcanoes, underwater volcanoes on the Pacific plate that are being subducted. These volcanoes are being consumed into the subduction system, and that's what a big one here. So there's lots of heterogeneity geometrically. The speed of sound waves in these seamounts is also abnormally low, which gives us a hint that there could be fluids. Amy Woodward has a lovely poster about this seismic experiment, so please speak to Amy later. Just before the pandemic, we had an exciting opportunity to drill into these seamounts to see what they're made of. This was done as part of the International Ocean Discovery Programme, IODP. So I spent 8 weeks on board this ship, the Joydes Resolution, where we drilled in water depths of 3 kilometers, a kilometer below the seabed, and recovered some cores to tell us what those seamounts are made of. What we discovered is that they're made of this volcaniclastic material, bits of basalt and other volcanic rocks with lots of gaps between them, lots of porosity. There's also lots of clay minerals here that lock up water. So these seamounts are effectively giant sponges, and they're bringing huge volumes of water down into the slow slip zone. So we've got all of the elements here that the laboratory models were suggesting are important. We've got fluids, we've got heterogeneity geometrically and in terms of the composition. So this is great. We've learned loads about the Gisborne slow slip patch. But a very legitimate question you could ask me is, well, how general is this? Do we always need fluids and heterogeneity for slow slip? Or is this very particular for the Gisborne region? So my research group think the answer to this question is going to come from satellite data. So satellite data is what discovered slow slip events in the first place. A few years ago, a data product was released called the European Ground Motion Service, or EGMS. This uses a technique called INSAR to measure movements of the ground. I'm not going to talk about INSAR anymore because Ben, our final speaker, is going to tell us all about it. The EGMS dataset is open source and it is fascinating. Go in, have a look if your house is going up or down. But the first thing we did when we saw it is to go to Greece. We know where all of the faults are in Greece, and we wanted to see how they were behaving. Some of the faults we know and love don't show any differential movement in this data set. They appear to be in that locked phase. Presumably, they're going to slip in a future earthquake. Some faults, though, that we know are slipping. So this is the Pisier fault. This side is going down. This side is going up. Between 2019 and 2022, it's had 1.5 centimeters of movement over 3 years, but there was no shaking. This is a slow slip event. Previously, the thinking was that to identify slow slip, you had to have one of those giant megathrust faults in order for the slow slip to be big enough for it to be detected. This data set shows no, we can see slow slip on these small faults. And that's exciting because these are at the surface. We don't have to go in boats and drill 3 kilometers underwater. These will be much easier to instrument and drill into if that's what we decided is useful. The fact this data set crosses the entire European continent also means we can statistically investigate how many of those faults are slow slipping versus locked. Is there a relationship with things like the fault size, the host rock type, whether there are thermal springs, when the last earthquake was? And the really interesting question is there any relationship between slow slip events and then a future typical earthquake occurring sometime later? So the title of my talk was, Did the Earth Move for You? And well, in slow slip events, yes, it does, but you don't feel it. This is a brand new discovery that's really shaken up the field of seismology. And we've still got an awful lot to learn about it and how it fits into the earthquake cycle and how it impacts seismic hazard. So I will leave it there and thank you for your attention.
Any questions for Becky?
Yeah, thank you so much, Becky. Any questions from the room or online? I guess just while everybody is summoning up their courage. Becky, what got you excited in faults and earthquakes to start with?
Good question. When I did my undergraduate, one of the field trips we went on was to the Gulf of Corinth. And it's just so spectacular that you can see the fault plains right there. So when I chose to do a PhD was advertised in the Gulf of Corinth. So I decided, that would be a really exciting place to go. I just so happened then to get a job in New Zealand, and that's how I got into slow slip. And I find it amazing that it's taken me full cycle. I started in Greece, I went to subduction zones, learned about slow slip, and now we found slow slip on my Greek faults. That's really lovely kind of circle.
Questions for Becky in the room? Oh, yeah. Scam frenzy.
So this may be a somewhat stupid question, but
There's no stupid questions.
with
It
a,
doesn't exist.
well, in a minute we'll know more. With a conventional earthquake, there's a release of energy, which obviously causes all the destruction. So with slow slip, is there a release of energy, and can you detect that in some way?
Yeah, so I mean, the energy is being released, but very slowly. So it doesn't cause the P waves, the S waves, the surface waves that we have with a typical earthquake to radiate. But the fault is still slipping. Sometimes slow slip events produce what's called tremor. So it's a little bit like volcanic tremor, if you've heard of volcanic tremor. Some slow slip events do the same, where there's kind of like a low frequency rumbling associated with them, but that doesn't always happen. But the big difference between conventional earthquakes is that they produce the P waves, the S waves, the surface waves. These don't. So in terms of the Richter scale, slow slip events would have a magnitude of 0 because there's no shaking. But on the moment magnitude scale, that's a measure of the kind of the area of the fault that slips. They have an equivalent moment magnitude number. Not a stupid question at all.
Yeah, it was just a simple question, actually. The Gisborne, obviously the slow slip in Gisborne, when was the last observed sort of actual earthquake, or as in sort of conventional earthquake?
Good question. So in Gisborne, the last earthquake that on the subduction megathrust that people felt was in 1947, but it wasn't so conventional. It was a moment magnitude around 5, not that big. It didn't really create any shaking. People reported feeling seasickness because the ground was kind of moving very slowly. But then there was a 10-meter high tsunami. So very, very strange. And we've done some work on it. And we think one of the reasons for the large tsunami is that the rupture was very slow. That slow rupture kind of enhanced the tsunami heights. So there was an earthquake. It was faster than a slow slip event. But if you think about typical earthquake, slow slip, it was kind of in the middle. So actually, I think we're realizing fault slip is on a spectrum from typical earthquakes to aseismic creep, and there are lots of different things in between. Thanks.
More questions?
Yeah, I was just wondering, apologies if you have already answered this, but in the rock record, do you see evidence of slow slip like you see for those like high deformation events? Do you still get like those shear zones, or is it just too slow that there isn't much to really look at?
Okay, good. Well, I guess in terms of the rock record, we don't see, the tsunami deposits or anything. That's what people tend to look at for looking at big megathrust earthquakes. And people have been looking for that in New Zealand to try and find evidence of when the last big conventional earthquake was. So with slow slip events, they don't produce that, so they wouldn't leave that behind. The fault zones themselves, though, there are places where we see subduction megathrust faults exhumed at the surface, ancient ones. And there is some work that people have suggested, some of those subduction zones are very wide, lots of shear bands, and people have suggested perhaps this could have been a megathrust fault that had slow slip on those, highly heterogeneous bands.
Yeah, hi Becky. My question is, I know as they're a relatively recent discovery, maybe the data set's a bit too small to say this, but is there a sort of upper limit on the size of the slow slip earthquakes?
Yeah, good question. The biggest we've found is moment magnitude 7, in places like Gisborne. They're also found in Japan, Cascadia. I don't think there's been one reported that's larger than a moment magnitude 7. What we need to do, or Valerie needs to do, wherever she is, we need to take this one and do some modeling to figure out what its equivalent moment magnitude is. We don't know that at the moment. So that will be exciting to see, how big a slow slip event on these extensional faults at the surface can we detect?
Fantastic. I think if you've got any more questions, hold them until our panel session at the end. Please put your hands together for the fantastic Becky Bell. And just while we swap over microphones, see if you can tell what all of our speakers have in common, other than they like the same kind of things about rocks. So we had Becky. Next, we've got Banusha in terms of our next speaker. And Banusha is not only originally an astrophysicist, but we will forgive you for that, because as of last week, she submitted her PhD thesis, which is pretty awesome. Okay, you're going to have to get used to this, in terms of, because it is really awesome. And Banusha's research is very much in the world of rock magnetism and also rock mechanics. So we're just switching over the slides at the moment. But while we do that, Banusha, why did you move from astrophysics into the world of rocks?
So I did a placement at Liverpool, actually, where I first got introduced to paleomagnetism, which is the study of the Earth's magnetic field, but the ancient magnetic field. And I thought it was so cool that you could use rocks to understand the past, and all the Earth's magnetic field history is recorded in that. And I thought I'd use physics to understand the solar system, the universe. Why not try and use physics to study the Earth? So I decided to switch to geophysics, and I don't regret it at all. And you get to do field work, which is really fun.
So just in terms of that fieldwork, if you want to see if the slides will click on. Oh, wow, there we go. So everyone, please put your hands together once again for the amazing Banusha. Thank you.
Thank you very much. So today I'll be talking to you guys about earthquake histories hidden in magnetism. So following on from Becky's great talk, the Earth experiences stress which deform rocks over different timescales. So for example, like tectonics, it takes millions of years to deform rocks and reshape them, whereas asteroid impact or earthquakes can instantaneously, within a second, deform and reshape rocks. Slow slip events that Becky mentioned before happen somewhere in between plate tectonics and earthquakes. And I've been focusing on earthquakes because they happen so frequently. They're a hazard to humans, like the disastrous event that happened in Myanmar last year. We also had a really bad earthquake in Turkey in 2023. And the problem with earthquakes is we can never predict them. And you're going to hear that a lot probably today. You can't predict them. But what we can do is study past earthquakes, look at ancient earthquakes in fault regions, and try and understand what causes earthquakes, what are the stresses, what are the direction, the spatial extent, and try and use that to understand upcoming future earthquakes. And to study past earthquakes, we can use magnetism, because rocks contain these tiny little magnetic grains like you've got on your fridge. You've got little magnets on your fridge. It's like that in your rocks. And these magnetic grains act like little time capsules that can withhold information about the Earth's magnetic field. Or, like, for example, if you have a volcanic eruption, you have a lava flowing, those tiny little magnetic grains align in the direction of the flow. But if I went to a volcanic region, say, there wasn't an erupting lava, I couldn't see the hot orange flow coming through, and it was just black rock all over me, how can I figure out the flow direction? So as a geophysicist or geologist, what you would do is take rock samples, and you would go to the lab and you would measure something called the magnetic susceptibility, which is you apply a magnetic field and you see how easily can I magnetize this rock in loads of different directions. And the direction where it magnetizes the easiest, its susceptibility so high, is in the direction of the magnetic grain. And we call this the principal susceptibility axis. The direction of this axis is the direction of the flow and the orientation of the grain. So we can use this to study flow direction of lava or magma, which is underground, or we can also look at sedimentary rocks, looking at marine ocean currents or fluvial deposits, so like river flow directions using magnetism. So if we can look at all of these geophysical events, can we look at earthquakes as well? Looking at the rupture direction, the stress, the direction. My entire PhD has been trying to figure out how stress affects the principal susceptibility axis, but without deforming the rock. So the grain itself doesn't change. Does the stress rotate the susceptibility axis without deforming the rock? So to do this and to understand earthquakes, I basically replicated earthquake conditions in the lab by squashing rocks and impacting rocks. So if we first consider squashing rocks, I took a cylindrical sample and measured the susceptibility axis before squashing it. And it's initially in the horizontal plane. So it's just in the horizontal plane. If you're a geophysicist, geologist, you might find it easier to look at an equal area projection, or you can just follow this arrow here. So when I place the sample into a squasher, I see that the susceptibility axis begins to rotate as I increase the amount of stress. And it starts to align with the stress direction. So it's completely changed the initial orientation and aligns with the stress. I take the sample out and wait a year and measure it again, and I see no change in the direction. It's completely recorded the stress orientation and stayed that way. Now, I thought this was really cool. I'm going to test it out more. So I decided to look at cubic samples. So I took a rock, filed it into a cube, and I thought if I compress it in one direction, so initially in the Z component, do I see it rotate to that direction? And it did. So every time I applied 88 megapascals of stress and rotated the cube and see if the direction always changes with the stress. And every time I applied it in the Y direction, X direction, every time it always changed. I thought, okay, so the susceptibility axis, without deforming the rock, without me changing the orientation of the grain, the actual magnetism is recording a stress signal. And it's sensitive to the stress magnitude, so the amount of stress I apply and the direction. So when I squash a rock, I'm applying stress really slowly. What happens when the stress is really fast, so instantaneous, like you would experience in an earthquake? So part of my PhD has been to build this dynamic instrument called the split Hopkinson pressure bar. And it's a 4-meter long instrument, and it consists of basically 3 bars: a striker bar, an incident bar, a transmission bar. And what I do is I place a sample in between the incident and transmission bar. I use a compressed air machine to pump air into the gas cylinder. Then I click this little striker button and it releases some air into the hose, into the gas gun. If we could take the video.
Let me quickly.
And the gas that's built up pushes the striker bar out.
Sorry about this.
So I just do that.
All right, ready to go?
So if you look here, the striker bar hits the incident bar. And the moment it starts to impact the incident bar, you create a little earthquake in the lab. There's stress waves that go through the bars into the sample. So the rock feels an earthquake, like in the field, but in the lab. And then the stress waves comes out of the sample into the transmission bar. And we use the strain gauges that are bonded to the bars, and they record on the computer and analyze the data. And if you can see here, there's a little cage here called a Helmholtz cage. I built this to control the magnetic field. So I can cancel out the Earth's field so nothing interferes. So I can make it 0, like what we'd experience on Mars or on the moon. Or I can apply a magnetic field parallel to the striker axis or perpendicular to control how the field interacts with the susceptibility axis. So I did loads of experiments on the 0 field conditions, 150 microtesla parallel to the striker axis, and 150 microtesla perpendicular to the striker axis. And what I noticed was the way the susceptibility axis rotates the stress axis is identical when I squash it as well. So the rate of the stress actually doesn't matter. It doesn't matter if it's fast or if it's slow. It also doesn't matter what field condition it is. It can be 0 or with a really strong field, and the susceptibility axis still rotates the same amount as I would see when I squash it. So this tells me that when I do these experiments, I can actually relate these response to the susceptibility axis, because it's so sensitive to the stress magnitude and direction. I can actually study it in the field and study the earthquake stresses as well. So if we have a fault core, so when, as Becky mentioned, when she had the 2 bricks together, when there's an earthquake, the stresses rupture out. And initially near the fault core where the earthquake happened, there's a lot of damage because there's a lot of high stresses around that region. As the stress propagates out, as the earthquake ruptures, the stress will be traveling at a reasonable speed, like similar to my impact experiments. Then if we go radially further out, the rocks experience like a squashing effect because the stress has dropped significantly, and it replicates my squashing experiments. So using my experiments and the response to Kmax, we can actually determine something called the paleo stress, which is basically ancient stress. So ancient stresses from ancient earthquakes. What that would involve is doing field work by collecting rock samples radially away from the fault core all the way out into the elastic rock. Because these effects are seen when the rocks are not deformed intact, we can go and drill rocks in the country rock and work towards the damaged zone. Then collecting those rocks, we can do some mechanical testing by squashing or impacting them, which then will give you a curve because the amount of squashing or impacting is equal to the amount of rotation. So using the samples that you collect in the field and your curve that you get from your experiments, you can actually determine the stress magnitude, the direction of old earthquakes, which is invisible to the naked eye because there's no deformation, but it's hidden in the magnetic signal inside those rock magnetic grains. And because you can capture the direction, we can actually go all the way back to the fault core and see where the fault slip happened as well. And in the fault slip, because the two rocks are sliding past each other, the heat and the friction causes melting, and that creates something called pseudo-tachyte. And you can actually use the pseudo-tachyte, the frictional melt, to age it, so you can determine how old this earthquake was, where the stress came from, how old the stress is as well. So altogether, you can use magnetism to study ancient earthquakes to help us understand what earthquake processes are, and then help us with future earthquakes and geohazard assessments. So here are my key takeaways, how we can use magnetism to quantify paleo stresses and how it can support geohazard assessments as well. Thank you.
Amazing, Banusha. Any questions from the room? Just while we're waiting for that, in terms of your field work, do you want to tell us a bit more about the field work that you did?
So I actually didn't do field work. That was just a photo I got on another field work. But what I did do was to test if this works. I actually studied columnar basalt. So has anyone been to Giant's Causeway in Ireland or Stafford? So there's column shaped rocks. They are basically fractures. Just like you see a massive fault, big fractures. I was looking at a smaller geological feature and looking at the stresses that are experienced from the fractures on a columnar basalt. And using this method, I actually determined the paleo stress. So the stresses that it experienced when it formed. So that was a way of testing to see if this would work. And it did work. And we could find loads of information about columnar joints and their formation. So now, after my PhD, someone will come in, hopefully, and they will do the field work, do this related to a fault region and test it out to see if it actually does work, which I hope it does.
Any questions in the room? In that case, I've got one. So I was wondering, you're looking at paleo earthquakes. I was wondering, does it have any implications for studying, could you see changes in stress occurring prior to an earthquake? And therefore, could it work as some sort of early warning system in the future?
Yeah, definitely. Because I think as the stress is building up, you should see relative changes in the susceptibility axis. So you can definitely use that before an earthquake ruptures, but you just have to go collect samples every time before you see changes. So yeah, you can study that for sure in fault regions.
Thank you, Banusha. I was just going to ask, what would happen if you've had multiple earthquakes in the same location over time? Can you see each individual earthquake, or is it just all merged into one earthquake?
That's a good question. So I think to separate different earthquake ruptures, you would have to basically just expand your field study. The bigger the field study, the more samples you collect, the higher resolution your data would be. And hopefully there's also different susceptibility parameters that you can use to distinguish between different ruptures, which I haven't gone into detail to because I don't want to complicate things, but you can look at the shape fabrics as well, which can distinguish different fault ruptures, which should help distinguish different earthquakes.
Questions for Banusha? Oh, yes.
I was intrigued by the instrument, just thinking my son would love to play with it. To what extent are there plans for instruments like these, or do you have to invent it yourself?
So the split bar Hopkinson has been around for years. People use it to study materials all the time. We use it to study strain rates on rocks and how, so like, for example, the San Andreas fault, we can see there's powdered rocks near the fault core. So what you would do is take sandstone near the San Andreas, do the impact experiment, see how it deforms, and you can link the strain rate to the earthquake. And that's how you would determine, oh, the San Andreas was 10 to the 3 per second strain rate. So people use it for to understand strain rates, but it's never done in a magnetic way. So I think I'm the first one to actually implement, because usually you would use it steel bars. So, but I had to change a lot of the metals, build a Helmholtz cage. A lot of work went into developing it so it can be used for magnetic studies as well. But yeah, it has been around for years.
But you've adapted it for magnetics. Yeah, cool. Thank you. That was pretty fun.
Any more questions in the room? One more. Okay.
One final question. In terms of the first piece of kit that you showed us, you called it a squasher.
Yeah.
Is it actually called a squasher?
I do call it the squasher. We all do the big squasher, but it's called a uniaxial hydraulic compressor.
I think a squasher's better.
Yeah. So yeah, it's just I just say squasher to anyone I talk to a conference talk to. But yeah, it's a uniaxial hydraulic compressor, which I use at UCL.
Fantastic. Well, Banusha, thank you so much. Everyone, hands together for the fabulous. Okay, so first up we had Becky, then we've had Banusha, now we've got Ben. So if your name begins with the letter B, don't worry, we'll be calling on you next because you'll be our next speaker. So Ben is actually an alumni of our department here in Earth Science and Engineering. He studied the Sci in geology between 2014 to 2018. He then went to a kind of mediocre university called Cambridge. And did his PhD there, and now he works as an INSAR scientist. So you heard Becky talk about INSAR a little bit earlier on, but this is what Ben does as his normal job now for a company called Catalyst. So please put your hands together for the fantastic Ben Conway-Jones. Thank you, Ben.
Awesome. Well, thanks for inviting me. I really appreciate it. My name is Ben. I'm going to talk a bit about geohazards and INSAR. Just a very quick nod to the company I work for. So we work with businesses and governments to identify and monitor risks in their assets. And that's my kind of day-to-day job, is using INSAR to help companies look at their assets, identify risks, especially to their critical infrastructure. So, as Becky's mentioned, this is INSAR. So INSAR uses satellite data. So we've got a nice GIF from the European Space Agency here of radar satellites orbiting the Earth, acquiring this radar data. It does it by emitting a radar signal. That signal bounces off the surface and returns back to the satellite. We can measure the strength of that response, which is what's shown in these black and white images. And that's really useful for looking at things like surface conditions. But what we're interested in is a component called the phase. So that's shown in this image in the bottom left-hand corner. So when a satellite emits its radar wave, bounces off the surface, comes back to the satellite, because it travels as a wave, when it comes back to the satellite, it will finish at a certain point on the waveform. That in itself isn't particularly useful. But what's really interesting is that when we wait for the satellite to come back overhead, say 6 days later on its next set of orbits, we then do the same thing. We ping down the wave, we look at where it finishes on the waveform. If we have an episode of subsidence, like in the bottom left-hand corner, that wave has slightly further to travel. And that means that when it comes back to the satellite, we have a slight shift in the waveform.
And that's what we see in the bottom right-hand corner here. So we call it the phase shift. And because we know the wavelength, the signal we emitted, we can determine millimetric displacement on the surface of the Earth using satellites that are orbiting hundreds of kilometers above that surface. So what I want to do is show you a bit of a geohazard case study looking at the Neshemi landslide, which occurred in 2026. This is Neshemi. It's a town in Sicily. You can see it sits on this pretty dramatic plateau. And that's because the geology here is a layer of sand over clays. Clay is much softer than sand. So instead of eroding from above, what you do is you erode into the clays in the sides. And that's how you get these really steep slopes and this flat plateau. Unfortunately, it also makes the area really prone to landslides, because when you have extreme precipitation, that water percolates into the sandstone, but it can't go any further because you have that impermeable clay. So the water just sits in the sandstone, weakening the strength of the rock until eventually you get a failure. And that's what happened in January of this year. So on the left-hand side, I have a before and after satellite image, and you can see that kind of entire area to the south of the town, about a kilometre by a kilometre block, moving by tens of meters. So this is a really massive, dramatic landslide. And a lot of the images in the media of the headscarp, where you can see this kind of 6 to 7 meter vertical drop. The implications of this were significant. Over 1,000 residents were evacuated, major access roads were closed, many minor roads are irreparable, hundreds of buildings were declared unsafe, and the Italian government freed up emergency funds of about 100 million euros, and damages are expected to exceed €1 billion. So what we wanted to know was, could we use INSAR, a tool for measuring deformation, to see if there were any precursor signals to this event? Do those signals kind of vary across the area, and how can we identify them in future? You actually see signals on a range of scales from days to months to years, but I'm going to focus on months for this presentation. So this is what an INSAR result looks like. The time period we're interested in is shown in the top left-hand corner. We're looking from July of 24 through to July of 25. The reason I was interested in this period was because we want to look at the last rainy season. Were there any lessons we could have learned from that last rainy season and brought into this year when we saw the extreme rainfall coming in the forecasts? Each dot is a measurement of vertical displacement. Green is stable, so you can see the majority of the town in the top right is stable. Red is subsidence, scaled to 50 millimeters. So the darkest red points are about 5 centimeters of subsidence over the course of that year-long period. And blue is uplift. So we can see that the town is broadly stable. But what's really interesting is we see lots of signal on the slope. There's lots of blues and reds. There's a lot going on here. Just to put you in kind of spatial context, this is that GIF I showed earlier, overlaid. So you can see where that headscarp opened up to the south of the town and that whole area that moves southwards. If I pick out just some of those subsidence points, those red points that we see on the slope, we can also look at displacement as a function of time. That's because we use the radar data that's acquired every 6 days as it flies over the same area of interest. And we can see that displacement here, this subsidence, isn't linear or constant. You actually get it in a number of small steps. And this is because that's when you have rainfall. So whenever you get rainfall, you get subsidence in this area. But then we're also seeing blue signals just slightly further south. So that's uplift. So why are we getting uplift associated with subsidence just a few tens of meters away? And what's really interesting is that when we look at the displacement patterns, what you see is that they show a very similar pattern, just with an opposite polarity. So nothing much happens till about January of 25 in the middle of this displacement plot. But then what we find is that in kind of March through into June of 25, you see these 2 steps of displacement. So how can this be? If we consider the area as a transect, so in the green, we have the topography going from the subsidence at which we see upslope and the uplift downslope. We have our INSAR results as a black line across here. And we get this by, we have slumping on the slope. So whenever you have this rotational slumping, you get subsidence to the top of the slump and then uplift at the bottom as that toe kind of pokes back up again. So this is really interesting because we could tell from as far as 18 months ahead of the failure that this is an area where we had slumping. So this is really unstable. It is not just there. Once I got my eye and I started to notice these pairs all over the place. So we see another pair here, we've got the same pattern with opposite polarity, again with an event in January and then another in May. Another over here, we can see again an event in May. And then finally one here where the headscarp eventually opened up. So this is really important information because we can tell you 18 months before it happens, this is a really unstable area. So hopefully you are somewhat convinced that INSAR is a powerful tool for identifying precursors to landslides. We can measure things like millimetric level displacement measurements, look at large coverage areas, and it's a fully remote technology, which makes it very safe and quite cost effective. But this isn't the first study to retroactively look at a landslide and identify precursors using INSAR. This is just a selection I pulled from Google Scholar. There's loads of people that have done a similar sort of study. So then the question is, why don't we have a worldwide or nationwide system whereby we're operationally detecting precursors to these landslides so that we can either stabilize them, put out monitoring equipment, or evacuate buildings and urban areas if necessary? Why doesn't that exist? And to do so, you need 5 components. Firstly, you need some data to work with. You need to process that data. You need to interpret it, make decisions based on it, and then actually put some actions into place. Beginning with data, we've got that. We've got loads of it. Sentinel-1 is a satellite that's been operating for about 10 years. It's a satellite I used to generate the case study I just showed. It's free and open access, which is brilliant, makes it very accessible, so we're good for data. Then there's the question of who should do the processing. Should academia be doing this? There's a vast amount of knowledge, but relatively limited resources. And if we want a workhorse system that's looking at the whole of Italy, for example, every 6 days for 5 years, that's not really what academia is suited to doing. Should it be public institutions who are publicly motivated, but they have limited knowledge and resources? Or should it be the private sector? We have knowledge and resources, but we don't work for free. And actually, none of these solutions are for free. So then who should pay for a system like that? Should it be public bodies and governments who are motivated for the public good, but have limited resources? Or should it be insurance companies and asset owners? That's my job most of the time, is working with asset owners and insurance companies, looking at a single asset. But actually, I think we can all agree that it would be a good thing to have a system that's monitoring precursors to landslides across entire nations. And importantly, as Becca's mentioned, this has been proven. We can process INSAR data at a continental scale. So this is EGMS, the European Ground Motion Service. It was a collaboration between all of those people I just talked about, academia and the private sector and the public sector. And it was all paid for by the European Environmental Agency. So again, I strongly encourage you to go and have a look at this. As an example, this is the RSM. We can see the Royal Albert Hall in the middle here. So these are INSAR points showing displacement. There's all green around here. It's pretty stable. If we look at the time series over the Royal School of Mines, we can see that we have a subsidence rate of 0.7 millimeters per year. And it's pretty flat. So I'm pretty confident that the RSM is going to stick around for another 175 years. The one point I'm going to disagree with Becky on is the one thing that you should not do is look at your own house, because it's never good news. So this is my house in Tunbridge, and we can see that it's moving somewhat more than the RSM is. It's subsiding by about 3 millimeters per year. And you can see that actually we've had some seasonal signals in the last few years, which explains some of the cracks in my living room that keep opening and closing with the seasons. So we've proven that we can process data at scale. But you'll see actually when you go into EGMS, there are lots of kind of numbers and options that you can select that require a degree of expertise. So I've chosen in the top left-hand corner descending data as opposed to ascending. What do they mean and why have I chosen that? In the next red box, we can see things like coherence, incidence angles, track angles. All of these affect how you interpret the data. And so there is a degree of expertise that's needed to actually take this massive volume of data and draw interpretations from it. You'll also notice that when you move from point to point, the results change pretty drastically. So if I move to a point that's about 2 meters away, you see that all of a sudden my house is not moving, but we've got a much larger seasonal signal in the last couple of years. So should you be looking at point to point? How do you interpret those differences? And so you kind of shift the question, who should be doing that interpretation? Should it be academia, public institutions, private sector? And then how do you scale that solution? I showed the example of Nashemi, and my job generally is interpreting data like that. It will take a couple of weeks to really get to grips with what I'm seeing and deliver my findings. But how do you deliver that at scale? How do you do it for the whole country every 6 days? And that's kind of, I think, where as a company, as a sector, we're kind of stuck, is how do we do this at scale? And that's why a system like this doesn't exist to monitor for precursors to landslides. We're capable of producing vast quantities of remote sensing data, but we aren't yet able to equip decision makers with the insights that they need. So hopefully that maybe starts a little bit of the discussion for the panel, because I'd be interested to hear people's views. But thank you very much for your time. And yeah, happy to take any questions.
Brilliant. Thank you very much, Ben. So Ben, you've shown that the Royal School of Mines building is fairly safe at the moment. Are there any other earth science and engineering departments around the country who are in trouble?
Yeah, I can't say I looked, but yeah, I think some of the Italian institutions I think I could take a look at. Yeah. I honestly couldn't tell you, although I'll be looking when I get home for sure. Yeah.
Hi Ben, great talk. I was wondering if there were any other Earth observation remote sensing techniques, let's say, that could work in tandem with INSAR for monitoring tailings dams or sort of man-made
Monitoring what, sorry?
tailings dams.
Oh, tailings dams. Yeah. So tailings dams is actually really interesting because they're one of the biggest kind of uptakers of INSAR. It's a really like proven commercial operational use of INSAR. They've really taken with it and run with it. There's lots of other things that we can do with tailings dams. So for example, you can use radar data to look at soil moisture. So you can look at seepage from your dams. You can also use things like change detection, which tell you whether you've had areas that have, for whatever reason, changed, whether it's looking at like vegetation. So obviously some of these tailings dams are intentionally vegetated, so you can map that vegetation over time, or similarly if it's been devegetated. We also have done things looking at, for example, illegal mining. So people illegally mining old tailings dams, and so going in and taking that material. And we can use change detection algorithms using both optical and radar data to look at these changes and to map the extent of them. So there's actually, quite a number of applications for tailings dams. And we generally kind of throw a lot at it. We look at it in kind of a lot of detail. So yeah, that's a great question.
Other questions for Ben? Oh, do you know?
Excellent talk, thank you. You just mentioned change detection, and I was just on your question of scalability, wondering in how much you dive into the wonderful and endless word of AI here, in terms of utilizing something which is more scalable than our human brain can sometimes do.
Yeah, I think that's the very natural next step, is to look at AI for this. For landslides, it's tricky to form things like training data sets, because you have to have a large enough bank of proven precursory signals that you can feed in as your training data set. And actually, I'm not convinced that such a large bank exists, or if it did, it would take time to do. The other thing is that landslides have there are a lot of mechanisms behind them. It could be things like faulting, it could also be the geology and things like weather events, rainfall. So there's lots of things that generate landslides. And so you'd have to account for that in your training model. You couldn't just put all of these mechanisms into a single model. There's one other thing I was going to say. Oh yeah, the other thing is I think it does still require a degree of interpretation. I think you could be able to maybe flag these areas as showing precursory signals, but it still takes a human to go in and understand what the geology is in the area, why those landslides might have occurred, and exactly what is noise and what isn't, and what's signal from other things. Because when you go on EGMS, you'll see all sorts of signals, and actually differentiating those from landslides, I think in many cases is difficult. So I think there still needs to be a level of human in the loop, at least at the moment, in that process. But I think AI is probably the answer for scalability. It's just hard. Yeah.
Any more questions for Ben?
Thanks. It's a fabulous talk. This is fabulous data, isn't it? I played with that Copernicus database. It's fun.
Yeah.
But I talk about a nationwide survey. You don't really need that, do you, for most places? UK, for instance, you look at the maps and there's a few areas that are moving. I didn't know they were moving, but they're moving. So it's a more tractable problem to monitor than saying the whole country or all of Europe, isn't it?
Yeah, I think that's true to an extent. I think there are reasons why you would do things on a national scale. So, for example, if you think about the railway network in the UK, we've got a big problem. There are lots of examples of derailed trains from landslides. And actually, that's a problem where you want to be monitoring the entire railway network across the whole country at the same time for these landslides. So I think it's not necessarily just kind of arbitrarily. You're probably right. We wouldn't arbitrarily monitor the entire country. But I think there are definitely use cases for monitoring at that scale. Things like railway networks, also things like bridges. So we recently looked at some bridges in Germany. many of which are showing signals. It's all aging infrastructure, many of which are showing signals of moving. And so it's a question then of how do we prioritize which bridges you go out and maintain, which ones you go out and replace. And so by monitoring kind of an entire country, processing that country's worth of data and isolating all the bridges, we can start to say which ones are moving the most and which ones require most attention. So it's probably true that we wouldn't process the whole country, look at the whole country, but I think there are problems and use cases for processing an entire country and focusing on particular areas of it and doing things at this scale.
Okay, one more question? Oh, hello. Sorry, I'll show you that was. I was just going to ask a quick question. So you mentioned that you've kind of got, actually there's like large data sets already out there and a lot of these satellites are kind of quite old. Is there a value in having like additional higher spec InSight instruments, or basically do you think that actually the kind of ability to collect the data, the tech that's already there is kind of good enough and it's just about kind of really getting the processing and interpretation right?
Yeah, it's a great question. Yeah, so a lot of the work we do is there are plenty of high resolution satellites out there. So the Sentinel data, which is that kind of workhorse satellite, has a spatial resolution of 20 meters. But we work with high resolution data that goes up to 3 meters, 1 meters. There's some that even go to 25 centimeters. So these are like super high res satellites that look at like a single building. So if you've got a skyscraper, for example, that you're worried about it leaning, so there's a really famous example from San Francisco, where you can use InSAR data to look at the leaning of the building. But you have to have high resolution data to achieve that because your 20 meter by 20 meter pixel doesn't get you very far. So there are use cases for high resolution data, but it costs money, it's expensive. So it's generally reserved for high value assets that require that level. But yeah, so that's one of the things that EGMS, as a sort of commercial company, when I was saying this to Becky, when we first saw EGMS, we thought, gosh, this is going to be the death of us. They're doing everything that we can do. But actually, there's that interpretation we provide. Also, EGMS is a springboard. We can identify areas where we see a bit of movement, and actually, they're high value assets. We want to hit them with some serious high resolution data and really get down into the patterns that we see. So yeah, I hope that answers your question.
Yeah, brilliant. Thank you. All right.
So what we're going to do now, that's not going to work, is it? So what we're going to do now is we're going to drop all the kit. We're going to go into a little panel session, but firstly, please give Ben a fantastic round of applause for his great talk. So just while we're turning on the lights and we're putting some chairs in place for our great speakers up on the panel, thank you. So as you notice, they're having to get their own chairs, but this is how great we are here. In case you haven't seen it, there's a little brochure around just sharing some of the information about our 175 years in existence, but also as well teeing up for what do the next 175 years look like? What could they look like? What should they look like? And to help us on with this, we've got more lectures that we're bringing to you over the next few months. So on the 16th of June, we're going to be joined by some of our fabulous lecturers, researchers, teachers, alumni who are going to be sharing some of their thoughts about raw materials. So think about exploring for some of those rocks that we need, those minerals and those metals that we need. Think about some of the processing. How do we process some of those minerals and metals, as well as how do we use things like AI to try and improve our ability to do all of that. So we've got a fantastic speaker lineup for you on the 16th of June. And then on the 21st of July, we're going to be talking about life and health. So yes, within geology, we talk about a lot of dead things in terms of our fossils, but we also talk about life and how we can use a lot of the innovations and the research to understand life in a better way. After the summer has finished, we'll then come back and we'll start talking about climate change, but also as well talking about things like planetary science as well. At the back of the room, you can see some fabulous images of a planet that's not our one. I'll let you guess which one it might be. Hint is maybe in the color in terms of what it is. So we do an awful lot of research with regards to that as well. But finally, with regards to certain areas or certain aspects that you can get involved in over the next month, on the 6th and 7th of June, we've got the Great Exhibition Road Festival. Now, Exhibition Road is also 175 years old, or at least from a festival perspective, this is what we've chosen to mark with regards to this year. And there are going to be literally thousands of people coming to Exhibition Road, to one of the world's largest science fairs. It's going to be truly awesome. So if you want to get involved in that, just come along on the 6th or the 7th of June or both. Come and find us. There are going to be lots of different stalls, stands, people doing scientific experiments. There's a silent disco with something to do with worms and fungi. If you want to come and check us out with regards to rocks, there are lots of games. You've got to fill up a shopping basket with all the materials that you need for all the different technology, etc. we have. So that's on the 6th and 7th of June here at Exhibition Road. For those of you online, feel free to come and join us. I guess we could stream it live if you wanted to, but I think it'd be more fun to come along in person. So now that we've got our panel together, Fred, do you have a question for our panelists to get us going?
For example, Becky, what actually got you into what actually got you into kind of earth sciences field, or what kind of led you down the path to
So I don't think that one's working.
It's not?
Yeah. Have you got the other one?
In that one. So I guess when I was growing up, I really enjoyed, my dad would take me fossil hunting on the beach. I really liked watching documentaries about volcanoes and earthquakes. When I got to school, I really enjoyed sciences and maths. But when it got to choosing, I knew I wanted to go to university. No one in my family had been to university before, but I knew I wanted to go. But I didn't love maths, physics, chemistry enough on their own to take them as a subject. So for a while, I was quite panicked. And then one day I was looking through a university prospectus, came across this topic I'd never heard of before, earth science. And it combined all of these things that I really loved and these topics that I enjoyed watching documentaries about. So yeah, in that single moment that, defined the direction that I was going to go. But again, like you were saying, I've never looked back since then.
Did anyone else want to speak that? I mean, Banusha, I guess you sort of spoke about it a little bit, didn't you? That you started off as an astrophysicist. So I guess what was it just that time in Liverpool that really kind of sparked it? And do you think you'll stay in an earth science context now, or not sure?
I think I would like to stay. I'm interested in climate science. I think that's the direction I would like to apply my physics to and look at more of the AI, machine learning kind of side in industry. But yeah, I think that's the direction I want to do something new, but still relate to my physics background and earth science, and yeah, continue that way.
Ben, do you want to?
I think the honest truth to me is I was looking at what A levels to do, and when I was looking around a sixth form college, geology students grabbed me and said, "You're doing geology," and I sort of was too scared to say no, so I took it as an A level, and then I loved it. It was brilliant, and I think it was exactly like Becky said. It was it's taking all these subjects I really loved, it's kind of maths, physics, but sort of felt a bit a bit remote, whereas actually geology was the grounding of it all, and then fieldwork's awesome. Fieldwork's so good. That kind of sold it. And I loved it so much at A level, I just carried it on into degree and beyond. Yeah, no, so that's my origin story.
Ben, perhaps you want to hold on to the microphone for a second, because so you obviously did your undergraduate here in the department. How have you seen the department change over the years? So we're 25 years old now as Earth Science and Engineering. Obviously, the Royal School of Mines is 175, but how have you seen things change, and how do you hope or anticipate they might change over the next 25 years?
Yeah, I think, gosh, yeah. I think there's a remarkable amount that stayed the same, which is a lot of the good stuff has stayed. And I think actually, I was part of a lot of the sports teams and really engaged in the union. And a lot of that, so we played with the old boys hockey game a few months ago, us versus the current students. And actually a lot of the camaraderie and the kind of sense of enjoyment stayed. But in terms of what's changed, I think obviously a lot of the masters that have come on board, I think they're exploring really interesting ideas and things that we didn't even consider as a possibility when we were undergrads. So I think that's a really exciting development as kind of someone that's now removed from it and a bit jealous that I didn't get to do some of the master's courses that are offered now. So that's exciting.
Just before you pass the microphone, yes, it's not too late to come back, Ben. But who won the hockey?
Oh, alumni.
That was gracious of you. Becky, how about yourself?
So I guess I'm the old timer up here. So this is the 16th year I've been in the department. So I guess I've seen lots of changes over that time. like Ben was saying, I guess a big swing has been we used to be really strong in petroleum, oil and gas. And there's certainly been, you know, a direction towards net zero. We've got lots of research now in things like carbon capture and storage, natural hydrogen. I do a lot of work in the offshore wind area. So that's been really exciting to see those skills, which are largely the same as what we used in the oil and gas industry, being used in renewable energy and these kind of future energy directions. The kind of rise of machine learning and AI, we've really embraced that, which I think is really exciting. And now we're kind of, you know, seen as kind of world leaders in that field with our new our master's programs. And the big change as well is the demographic. So when I started here 16 years ago, it was, you know, very, very male dominated, both in terms of staff and students. And now we've got to a point where some of our undergraduate and master's programs are 50-50. So yeah, things have changed in a good way. Certainly, yeah, the culture here is really lovely now.
Becky, Banusha.
Well, I've only been here for 4 years.
It's okay.
But no, I agree. I think coming from physics, I think one thing I really realized about earth science was the gender balance. I find it quite astonishing how there is nearly 50-50 male, female, like gender balance. And I think that's a really great thing. And I hope that does spread to the other sciences. I hope everyone learns from earth sciences that this is how it should be. And I think this department especially, it's going in the right direction with machine learning, AI, the research. And I really like how we're still doing field work. I think it's really important as a geoscience to continue field work, because we need to study the geology and the geophysics out in the field and then come to the lab or to our computer to model it, to do the machine learning side of things. So I think I really like how the department's going in that direction, embracing all parts of sciences and moving forward.
Brilliant. Just before we open up to the floor, so the title of tonight's series of lectures was Geohazards. Now, we've spoken quite a lot about faults, we've spoken quite a lot about earthquakes, the movement of land, but that's not all that might be encompassed in the world of geohazards. I wonder, Becky, if we come back to yourself, maybe think, right, well, what other kind of geohazards there might be? And if you didn't study things like earthquakes, what's your next favorite geohazard?
Okay. Well, I guess the other geohazards, the bit, I don't know if it's the big four or the big five or whatever. Volcanoes, we haven't spoken about them, so that's a very obvious geohazard that's not been mentioned. I guess what interests me about earthquakes is that they can cause many cascading geohazards. So an earthquake can create landslides, it can create tsunami. There's even some, you know, rare reports that they can trigger volcanic eruptions as well. So that's quite an exciting field, that kind of geohazard cascading. It's not just one or the other. They you know, can all be linked.
Ben, have you got anything to add?
I'm not sure I do, honestly. I think that sort of covers it. Yeah, sorry, that's a very rubbish answer. But
so you don't like volcanoes then?
Particularly, no. Yeah. They're really interesting things to study with INSAR as well. You can kind of look at the inflating and deflating a lot of the chambers. So there's a really interesting application, one that is not as well studied, I'd probably say, as faulting and landslides. But yeah, no, there are plenty of really interesting applications for it, and I think that's one of them that's perhaps underexplored.
Banusha, anything to add from an astrophysics background?
I guess another geohazard is impact craters.
Yes.
Being hit by an asteroid.
Did you know that's an asteroid that passed really close by last night?
No.
It so news as me. But there was a 20-kilometer asteroid, just like it was quarter of the distance between the moon and the Earth.
Wow, I didn't.
Near miss.
But yeah, but they don't happen as frequently. We don't get hit by them. Thank God. But yeah, no, I think earthquakes, impact craters are my favorite geohazards.
Awesome. Opening up to the audience, any questions from the room for our fabulous panel? Anything else about earthquakes, faulting? Yes, sir.
I actually have a slightly wider question, so apologies for it. But I would say employability is obviously on the minds of pretty much every undergrad, I would suspect, and postgrad in the market at the moment. And so I'd be really curious to get your idea in the context of your studies and what you're seeing in the wider world where you think the real sort of growth areas for research, employability may be over the next sort of cycle of 3 to 7 years, maybe.
So coming from a sort of remote sensing world, if I come answer it from that point of view, I was at a conference at ESA last week, and there's a very interesting plot of satellites going into the atmosphere, exponentially increasing, but the money that's being made from satellite data is kind of plateauing a bit, and it kind of speaks to the point that I was just talking about, where we're kind of struggling to interpret a lot of this data at scale, and I think in terms of employability, it's taking a lot of the academic studies to what you're learning here and thinking about how do I apply this in the real world? How can this add value to someone who doesn't necessarily understand it? So I think thinking beyond the kind of pure academic theoretical side of what you're looking at, but also think, how can I apply this? How can I add value to this? How can I provide value for other people? So I think having that, thinking about that next step whenever you're during your studies, I think is a really valuable thing to be able to do, and it's a very employable skill, I think. But yeah, generally in the space sector, it's growing, and it needs people that can interpret data and provide value and insights, and is capable of really critical thinking. So I think that's what I'd say is a really valuable skill you can learn.
Yeah, I also think the Earth observation side has lots of potential future uses, and that's really, really exciting. I guess another one is the renewable energy industry and moving in that direction to ensure our energy security, not just for the UK, but, other countries as well. So, even doing things like developing solar farms, you still need to know about the ground. You need to know if it's going up or down. Certainly larger scale infrastructure like offshore wind, that requires lots of these kind of geological, geophysical skills. This is now thinking completely off my head from all of the things we've talked about. I think we've kind of shown you in this room a number of different ways in which maybe we could identify precursors for things like landslides, maybe even earthquakes, but it's going to take money. All of these things require collecting data, interpreting it. It's kind of seems like we're coming to a point where the scientific knowledge is there, but it requires investment, people to really get on board with this, to put it all together. So I'm not sure who out there is listening, but yeah, I didn't actually know who was going to be speaking or what we'd be speaking about, but I think it's all really nicely linking up to, there's a really bright future here, but it is going to require some investment to get all of these things working. So maybe in the future we will be able to, I say that these disasters might happen before they do.
I think, yeah.
I was just, if I may, one thing I was thinking about in terms of employability as well is that, you mentioned it, Banusha, in terms of what we'd still do is a lot of field work. And at the moment, robots are still not very good at kind of going out in the field, collecting primary data, interpreting that data. And so I actually think in terms of across lots of different sciences, to some extent, at least for now, geology or the sort of fundamental skills of geology and geophysics are quite kind of AI proof, or at least you're still going to need a human in the loop, as Ben was saying, for a lot of these industries, whether it's kind of mineral exploration, and we're going to need a lot more of successful mineral exploration in the future. So yeah, I don't know, I think in terms of employability, I think geology in a relative sense is definitely kind of moving up in the world in that sense.
So something else about geology, geophysics, all of the earth sciences is they're really interdisciplinary. So they combine lots of different fields. They teach you lots of different skills. It's like being a detective. We don't have all of the information. We have to piece it together. So all of those things are really transferable. So you'll find, many geoscientists go into all kinds of different directions as well. It's a really exciting field for developing those kind of critical thinking and problem solving skills.
I think just a couple of other areas, if you've got a degree or you're interested in this kind of background. So, I know that this sounds really fascinating and exciting, but insurance. So there's a huge world of insurance with regards to geohazards, etc. And also a lot of the work that we've just been talking about here have actually helped the insurance sector to understand the risks associated with those hazards. And then also things like disaster recovery. So I've spent a lot of time in different UN type areas. So disaster relief, you always need someone who actually understands something about what's going on in the rock beneath our feet as well, because just because you've had one earthquake Doesn't mean to say there ain't going to be another one, etc. Or what can we learn from all of that as well? So there's lots of different career paths that come from there. Cool. Yes.
I think you're absolutely right in what you just said, but the big problem is that there remains a huge disconnect between the sectors that really suffer from major disasters, fiscal regimes, global economy, and the insurance industry, and the earth science industry, where we can do something to help them, but we don't have the connections that make our work understood and give it the value that it really carries. And I don't know that, that requires a different set of skills, because we like knocking rocks and they like spreadsheets, and we need people to balance between those two things in order to make them combine and for us to be effective.
Sounds like something.
Yeah. Cheers, guys. Yeah, I think it's an excellent point. I think that, I think there needs to be some meeting in the middle. I think we can't expect people who like spreadsheets to understand rocks. I think we need to do, speaking for my industry in remote sensing and InSAR, we need to do a better job of understanding what they want to hear and say in a way they understand. An example, a really interesting example I heard last week was Google Maps, right? We all want to know the answer to the question, where are we? And we get a blue dot and it tells us where we are. And we think, brilliant, right? We don't care about the GNSS satellites that tell us how we generate that data. We don't care about the errors associated. We just want to know the answer to the question of where are we? And so I think we need to do a better job of understanding what the industry wants and what answers we need to provide them and what questions they're asking. Rather than explaining necessarily the ins and outs of the rocks, we actually need to understand what they want to hear and be able to communicate our science in a way that is better understood by them. And I don't think that's something that we do particularly well in remote sensing, perhaps earth science more widely. And that's a skill that we need to be learning to apply it. The other thing I quickly mentioned on like the financing point is that rather than thinking about things in terms of we have to pay for more monitoring, actually I talked about the Italian example where damages exceed €1 billion. If perhaps some of those damages could have been avoided by putting in slope stability measures or extra monitoring, then actually the monitoring that we provide will save them orders of magnitude more than they're spending these monitoring. And I think we actually need to pitch ourselves more as a money saving exercise than we do as a kind of extra thing that you need to pay for. So I think we need to think a bit more sort of smartly about how we pitch ourselves and how we communicate with industry better. I think that's what I'd say. I don't know if anyone's got anything to add.
So, I mean, maybe to follow up on that. So I was going to kind of ask a question about how teaching in earth science, but also I guess geohazards sort of has changed in the sort of the past 20 years, and how much change in the future. But I guess leading into that, it's like, do you think we actually kind of need to teach our students a bit more of that kind of applied end of things in the degree courses? And is that something that's currently, I mean, in terms of your interactions with people in industry, is that something that is kind of voiced as a current issue, or not so much?
The honest truth is I don't know. I think it's achievable I think as long as you're teaching critical thinking and the ability to communicate with people, I think you'll get there. So I don't know if it necessarily needs to be explicitly taught, but I think it is really helpful to get an idea of industries and applications of what we're learning, so that you can more efficiently, understand and communicate what you're doing. I think thinking about things in a sort of the applications of the industry and the way that people are interested. So not just geohazards, we can save lives. It's more like, why is this valuable to the insurance sector? Why is this valuable to finance? And think a bit more kind of beyond the sort of first step of applications of a given subject. So I think it's something that, it probably needs improving on how we communicate that. But also, if you just teach critical thinking and good communication and empathy, then I think you can start to get a good way there.
We have kind of kicked around the idea of having a sandbox where inviting people from the insurance industry, telling them what we do, trying to find out the problems they're interested in. So yeah, again, if there are anyone for the insurance industry in the room, then that's something that we'd be keen to talk about. I don't know the statistics, but quite a few of our undergraduates do go to work in the insurance industry. So we are getting geos into the industry. It's quite a popular career path.
I would add, though, that they're in technical roles. They're often not in the roles where you're sort of spreadsheets. Exactly. Yeah. So you're still missing that link between people that are doing the technical side, but then the spreadsheets. And I think that's that gap is where you need geos. And I think at the moment, too many people are going into technical, if that's fair.
I mean, the communication challenge is the predictability. It's turning the science, which is observations as to what's happened, into useful predictions to the future, and that's kind of the challenge for the team and for the subject. So, in the spirit of that, and a light-hearted question, would the panel like to give examples of their favorite predictive methods for earthquakes that don't work?
Ooh. So you may have heard there's been this study in California on the San Andreas fault for many, many years, where they basically monitored everything they could think of that could possibly be related to an earthquake, and none of the methods worked. I think they even kind of monitored animal behavior, kind of, behavior of dogs, behavior of cows, but they found no relationship. In Greece, where we work, there's some really interesting ancient texts of all of the kind of rats leaving cities before big earthquakes. But yeah, in this San Andreas project, there was no animal behavior relationship. So, Banusha?
I don't know any other methods that don't work. I hope magnetism works. It's not been tested properly on a FOV. I hope it works. Well, like the reason why we looked into magnetism was seismometers. You can detect the earthquake, but you can't tell anything more than like the actual earthquake. So you can't really look at the stress magnitude or the direction, because seismometers work horizontally or vertically. So I think that's where this magnetism comes in as a really good tool to look at different orientations. But again, yeah. So I'm going to say seismometers. Just
Yeah. I don't have a huge amount to add, but I think flooded seismometers, deploying a seismometer, finding out it's flooded and hasn't worked the entire time you deployed it there, I think that's the worst way to not detect earthquakes.
So, Becky, you mentioned something there about, okay, what would be really useful is maybe if we set up the sandbox, we bring in people from insurance and we try and kind of bridge that gap from the kind of that technical aspects of trying to understand uncertainty, going into that world where people can actually begin to calculate, well, what's that level of risk or potential loss, for example, or gain that we could put on all of that. Just thinking again to the next 25 years, is there anything else you think that we as a department could or should be doing or cultivating or looking to maybe explore that can really make more use of this amazing research that's been done into geohazards?
It's a big question. I mean, again, I really loved your slide, Ben, when you kind of, explained what academia can offer, what industry can offer. And we are often quite siloed, and there is a lot I think we could do together in addressing some of these huge global challenges, like precursors to landslides, precursors to earthquakes, precursors to volcanic eruptions. That's going to take all of us together, not just, academia or industry alone. But again, it's communication, it's bringing those groups together, trying to get them to speak the same language. And, just finding that thing which is going to motivate everyone to kind of get on board.
Ben, from your perspective?
Yeah, I completely agree. I think the EGMS is a fantastic example of what happens when you collaborate across academia into industry and public sector as well. I think, yeah, as the academic, if academia can keep exploring those collaborations, I think that's really powerful. I also think that in the professional world, we do spend quite a lot of time reading academic papers and understanding what the latest kind of technical innovations are. But I think it also needs to work, or it's very helpful if it works the other way. So understand what's going on in the industry, what's driving end user engagements, what are people paying for, not necessarily to try and, market to that, but to understand user needs and where the kind of wider interest is. So I think just keep engaging, keep that engagement going both ways, I think is really powerful. And not necessarily just talking to people, actually going online, following people on LinkedIn, seeing which conferences people are going to, what they're learning. I think that's all really valuable. Yeah.
And Banusha, as someone who's just handed in her PhD thesis, you've already mentioned climate as being one of those areas that you might like to go into, but where would you like to see this department going in the next 25 years?
I think what they're doing currently is really good, and I think they should maintain it, continue the field work, the moving away from petroleum and stuff, and looking into climate sciences, carbon storage, looking at health in the earth as well, looking after it, kind of research. I think, yeah, it's going in the right direction. I hope it continues to do that and not forget the old geophysics and geology as well.
Brilliant. Fred, any final words from yourself?
No final words from me. I think it's now just gone past. So if we can all thank our speakers again for doing a fantastic job. Drinks.
And we have drinks next door in G35, so please feel free to come and join us there. Or if you need to Scarpa, don't worry, we'll be back again on Tuesday, the 16th of June, to be talking about raw materials. Or we'll see you at the Great Exhibition Road Festival on the 6th and 7th of June. Thank you very, very much to Fred, to Gege, and to the rest of the team for putting everything together tonight. Thank you. Round of applause.